Well, okay. So defining relations and their constraints are one of the components of database design, and database design, or design in general, is going to be a sort of theme that permeates throughout this module. Design of databases, design of applications, design of visualizations, etc., ways to interact. So design is something that we're going to be meeting throughout this module in various places. Between the conceptual, logical, and physical design of the system. I'm just mentioning a process called normalization here. We're going to have a lecture on normalization later in the week. But this is just to say that the sort of designing of the relations and tables, as we've discussed, is just the very start of design. There is also a relational table design. There is a formal process called normalization, which is a formal process of organizing fields and relationships to minimize redundancy of data, redundancy being duplication of data, and the dependency between items of data in a database. And we're going to be meeting that later on. So just saying that there's this theme of design that we're going to meet at various points in the module. So that's kind of really the basic theory of relational databases, or it's not actually, let's say, so I've given you, what we've done in the first half is kind of giving you an overview of kind of how the relational database models from a sort of theoretical kind of perspective. What I haven't done at all this morning is to talk about the relational logic, predicate logic that underlies the relational model. You've got this data in tables. Well, what is the logic and maths behind how we combine those together? And I'm not actually going to talk about that much in lectures at all. I might mention some of it next week briefly, but if you look in the notes, we were talking about the notes in the break, briefly in the break there. If you look at the notes, it goes into more detail on the underlying logic, predicate logic of the relational model. So, we've talked about I've sort of talked about the sort of theoretical underlying design of the relational model. Now we're going to move on to relational database management systems a bit more, the software that implement the relational model to a greater or lesser degree. So RDBMSs have three types of languages, programming languages, things that you have to do, or the languages can be divided into three. You need a language to define data, a data definition, what's called a data definition language, to define the database. And that language allows you to define relations, tables, fields, domains, data types, constraints, indices. We'll talk about indices a bit more in a minute, indexes a bit more in a minute. And this is also might be called a data description language. So you need a language for defining your database. You need what's called a data control language, a language that defines users, groups, and permissions on those users, so that controls access to the database. And you also need a data manipulation language that allows you to add, delete, update, and query data stored in your database as defined by your data description language. So you've got three types of things to do. You've got defining your database, controlling access to your database, and actually interacting with the data in your database. And luckily for us, or generally, there is this thing called SQL, Structured Query Language, which is an ISO, an International Standards Organization standard for interacting with relational databases, and that implements both the data definition, control, and manipulation functions within a single language. So you don't have to learn 3 different languages. There is one language called SQL that allows you to do all the data definition, control, and manipulation functions. And indeed, we're going to start doing some SQL and loading some data into database this afternoon. So SQL, it's quite it's a big comprehensive language, but when we're primarily interested in, from a query perspective here, just a little bit. Next week's lecture is entirely about SQL, a whole lecture on SQL next week. But SQL primarily works with select statements which gather information from data from one or more relations and return a result. So in SQL, the select statement is the one that you use to return data from your database. So this is the data query language, basically. And it uses relational logic, mathematics, and text and binary processing to transform the data stored in relations and return them to you, the user. As I say, I'll go into a little bit on what relational logic is and things like that, I think, next week, but I'm going to stay off it now. SQL select statements always return a new relation, a table, or give an error. So you only ever get a table out of a relational database. A relational database is made of tables and returns tables. If no matches, so if your query, your select statement, your query, doesn't match any data, there's no data in your database that matches that, what you get returned is an empty relation. So you get a table with no columns and no rows returned, basically. So you just get an empty result. If your query is just going to return one value, so for example, I've got a set of temperature records every day for a month, and I want to know the maximum temperature within the month, 31 records, one day for each temperature, then I would do something like select max temperature, and what I get back returned is I would get a single value, 26 say, but it's returned as a relation with one field and one row containing that. So you either get an error or you get a table returned. Thing about queries is that they are live. The information is taken directly from the underlying relations. So if the data in the database changes, so does the query results. So if you've got a constantly changing database, every time, let's say something like Amazon, you run how many sales have we had today query, it's going to be, every time you run it, you're going to get a larger number, presuming there's more sales happen. So that's something to bear in mind. You run a query today, you may not get the same results as the same query yesterday because the underlying data has changed. And queries may be saved as what we call views. It's just a saved version of the query. You're going to be writing select queries, you're going to be writing views, you're going to be doing all this kind of stuff in the next couple of weeks in the practicals. Queries need to access data in the tuples, or all tuples in the relation. So if we need to undertake a query on a relation, potentially, we need to scan all the tuples in the relations to undertake that query. So we have a table of temperatures, and we want to know all the temperatures that are above 20 degrees C. The only way we can do that is by checking the temperature in every row in the table. And as the tables get larger, the queries get slower and slower and slower. So what the relational model supports, or relational databases support, is indexes on fields, more than one fields. And these indexes speed up the queries by providing shortcuts to accessing the records. And indexes rather than indices. That's bad typing. That's the wrong word. It should be indexes are often tree structures that must be rebuilt to reflect data updates. Remember what I was saying about the problems of tree structures as a database structure. Well, in the relational model, we use tree structures as ways of indexing data in the relations, in the tables. They're not the only, trees aren't the only type of indices. There are other indexes that aren't tree structures, but the most commonly used one index is the B tree or versions of the B tree. And we'll just show you a quick example of a B tree index here. So here's our B tree, a B tree of a field which contains people's ages as an integer. Okay? So what happens is you get a table and you build a B tree index on a table. And what it does is the index builder will go through all the rows in the table and find the age for each tuple, each record. And then what it does is it uses a tree structure to index those values. Okay, so here's an example. So I want to know all records where the age of the person is greater than 5 and less than 6. Okay, to do that without an index, B tree index, I would have to search through all the records in the table to get the answer. However, with my B tree, we can do it really, really quickly. So I won't bother as to how the B tree is actually built, because it's optimized in optimization algorithms. But basically, you start at the root node. And the root node, basically, it orders the values in the table and then splits them up to make the tree. So I want all the records between ages 5 and 6. So the B tree, we start at the root node. And the root node has a value of 13. And basically, all the ages up to 13 go off this way onto this node. All the values above 13 go that way to that node. Okay, so I want an age between 5 and 6. Well, it's less than 13, so we go to this node here at the intermediate level. Okay, this node has 3 splits. This one just has 2 splits, less than 13, more than 13. This one has 3 splits, one between 4 up to 4, next between 4 and 7. Okay, sorry, between up to 4, between 4 and 7, and then 7 up to 13. Okay, so we're wanting between 5 and 6, which is between 4 and 7, which is the middle one, takes us down here. Between 5 and 6 is here. So this cell here, this will link to a list of all the row IDs, the primary key values, basically the row IDs that match, that have values between 5 and 6. So instead of searching every row in the table, we've got the result through 1, 2, 3 queries, and we've got our result, our list of rows. So we've had to do 3 things instead of perhaps 500 things, or 1,000 things, or 10,000 things. So it really speeds up, indices speed up access to the data records in a table. And you can go down the directions. We'll have more on indexes at the moment. Just understand that this is a simple example of the way indices operate, and that indices are about speeding up queries, the results of queries. Okay. So we've got the basic. So SQL is a language that provides. It's got the data definition. It's got your data manipulation. It's got your data controls. But there are things that you want to do that SQL doesn't do. with your things you want to do with your database that SQL maybe doesn't support. So relational database management systems support functions that allow you to customize and automate your relational database through either internally defined database functions, defining your own functions within the database, or by writing programs outside of the database that then access information in the database and manipulate it from an external program. So, just to say, database functions tend to be specified within the database itself. So it's a program that's written inside the database, within the database itself. It extends the SQL syntax that allow, for example, allowing arguments to be passed into SQL queries. Some of this will become more understandable as you get practical experience of writing SQL. But just bear in mind that there are certain things that SQL can't do or doesn't do very well that are better done by other programs by having additional programming functionality. For example, from Postgres, you can call programs, you can write a database function that will call a program written in another language. So if you've written in Perl, R, the statistics program language, anybody heard of R, used R? It's a good thing to have a look at. Great for graphs, statistics, stuff like that. So you can write a program in R or in Python or Perl and then use a database function to call that program. That program then runs and does something on the data in the database, etc., etc. So you can extend the functionality of your database by writing your own functions. That's the basic take-home there. But you can also, and these types of database functions extending SQL tend to be a non-standard between databases, as is there is no international standard for extending SQL into a full programming language, which is what's required. And then I mentioned there are also scripts, which are programs written outside of the database and run outside of the database that basically hook in to the database, execute programs within the database and for some reason or other. For example, backup routines, periodic data dumps, all sorts of things like that. So there's two ways. You can either write programs within the database as a database functions, or you can write programs outside the database that access information in the database. How do you access your relational database system? Well, there is the jolly command line. Okay, so Postgres has a command line function, and I think as part of the practical I get you to open the command line and have a little play with it, but it's not what I generally use for managing and interacting with my Postgres databases, although I can use this if you want. So as command line, hopefully you're all familiar with the idea of a command line. Basically, you just get a line here, and then you start typing your select commands or whatever on the command line here, and it just gets returned. Here's an example of a table being returned. Select star, here's some SQL. Select star, star means all columns from an employee table, and that's the kind of return we get just as a sort of little text in our text window. However, it's not the most friendly of things. Even I don't particularly like command lines if I can avoid them. They're quick, I'll give them that, and if you're skilled at them, they can be the quickest way of interacting with things. What I tend to use and what you're going to be using throughout most of this for the practicals is pgadmin 3 client. So the database itself runs kind of in the background on your computer. So depending on what kind of operating system you're running, so for example in Windows, it runs as what's called a Windows service. It's something that runs in the background on your computer. It's a Windows service. In Linux or Unix operating system, it would be called a daemon. It'll be running as a daemon in the background. I have no idea what they call it in Apple, world of Apple. but basically these are programs that are running on your computer in the background. And what the clients do, client programs are applications that then plug in on top of that working database. So your database is running there, and the client is a separate program that hooks in to the database and provides access to it. And pgadmin 3 is the program that comes wrapped with Postgres, and is a good client application for writing, for managing your database and writing your queries. And this is what it kind of looks like, and you'll see this afternoon. Here's my database server, Postgres. Here's my list of my databases in my Postgres databases. Here I'm inside a database called Kingston Env, which contains 3 of these schemas. Schemas are equivalent of folders that within a database that you can store tables in. In the env schema, I've got 9 tables, one called A road, B road, district, minor road, monitor sites. I've got a whole load of tables in there. And as you can see, there's also this public schema. This public schema contains 892 functions, defined functions. Those are the 892 functions that were in Postgres 1 point whatever it was. So these are the spatial functions for Postgres. We're now in, this is in version 1. Version 2 now has over 1,000 functions defined in it. Okay, and it also contains 1 table and 4 views down here. You can also things like trigger functions. So it's a nice graphical way of accessing all the stuff in your, or most of the stuff in your database. Okay. Here on the right-hand side, see we're highlighting those 892 functions. Well, here they are listed out. It's just like a Windows Explorer, but it's within the database. And we can see these are the functions, std within. So that's a function that will calculate the distance, a within function. That's a spatial function to get a within function. So it's doing a buffer on a geometry and then finding all the other geometries that are within a certain buffer distance of another geometry. So we've got the list of all these functions. You can see. And this is what it looks like when you do SQL. It has an SQL window, so we can type in our SQL commands. This is just a text file. It's got a .sql extension it's saved as, and I can write my SQL queries. I can write some commentary so I remember what they are. I can highlight the SQL, press run, and then I get my return. So slightly friendlier than the command line, but essentially doing exactly the same thing. So that's going to be your main interface onto Postgres. Unless you want to go command line, in which case, great. That's up to you. I don't mind. But this is generally more accessible, and I find it friendly. Also notice this, you get useful things like context-based highlighting here, which is really useful. So we can see that the SQL commands are in blue, the field names are in purple, the names of relations are in black. So there's also, that's helpful for seeing whether it can detect whether you've got correctly formatted or what the text is meant to be referring to. Unsurprisingly, not every user wants to write SQL. In fact, most database users don't even know about SQL, unsurprisingly, and they use graphical, and they tend to use more graphical-based interfaces onto the database. And these are generally called database forms. And a database form is an interface onto a database designed to meet a specific set of user needs. So, example, a customer services department might want to query, view, edit, and enter customer and order data on a record-by-record basis. I ring up, I want to order something, the person on the end of the phone enters in a new order. I then, for whatever reason, maybe I've given them a wrong address, I want it delivered to another address, I ring them up, they have to get that information back up for that order, change the delivery address, things like that. A supplies department wants a different view onto the database. It wants to, so for example, they want to know how many objects, what contents they've got in their databases. They want to order new supplies from other companies. So they have a different set of requirements, a different set of database forms accessing the same database. And maybe management isn't interested in individual sales, but they're interested in summary performance statistics across the organisation. So different forms allow customization for different users. And these can be built. Some relational database systems provide form-based systems as part of the database out of a box, so to speak. So Microsoft Access you can build forms in Microsoft Access. Now, this one was probably built in what's called VBA, which was Visual Basic for Applications, but Visual Basic for Applications, I believe, has now been discontinued within Microsoft, and it's probably not VBA, but it's something similar to VBA that isn't quite VBA nowadays. Anyway, you can build these forms. You can run this from within your Access database. You define your form, you run your VBA form, and you can enter your data. Similarly, Oracle, industrial strength, probably the biggest relational database in the world, the largest number of sales, Oracle, has its own form-based system, so you can build forms. It has an Oracle form system. So you might have forms, be able to define forms within your database, like you can define functions within your database. Or increasingly, people are building web-based forms or using external form building systems, software that then plug into the database. So, it's just a case of where this software is being stored and managed rather than what it does. So here's an example. This is a web-based HTML forms with an embedded map as well. Very simple. We can put in a postcode. We can go to the postcode. It gives us a latitude and a longitude for our postcode. Simple web-based form. And that's what we're going to be doing in the second, after Christmas, is we're going to start building web-based forms, HTML forms, which access the data in the database. So that's forms, different views onto the database. The other thing is database reports. Database reports allow you to summarize and present data in a database as a document. And records can be grouped into levels and summaries calculated for different groups. Each time a report is run, it uses the latest data from the underlying query, not surprising. What are forms like? Well, an online form might look like this. So this is an online form. It's not a document per se, but it's a sort of digital document. And we've got each room in a hotel. We've got who stayed, for what period, what amount of income was made on the room, and the total amount of income on the room on each room here. So if you're managing your hotel, you can see whether your high-end rooms are returning large amounts of money compared with your low-end rooms, for example. And this sort of stuff can be printed out easy enough. Increasingly, while it's useful sometimes to see the individual records, often the case is people aren't necessarily interested in the underlying records, individual records or summaries of the individual records. They prefer to see things graphically displayed, and reports and forms indeed can contain all sorts of graphic representations of data as well as the actual figures coming out of the database. So here's an example. We're looking at sales through time. This is on an hourly basis. Doesn't really matter what it's about, but here you can see this is built in the Oracle Enterprise Manager system. So this is the Oracle database, and we can see that we can view various reports, and these reports, rather than returning figures, are returning graphs as well as the figures in the database. You can, with modern software libraries, these kinds of things are becoming really easy to construct. Okay, so just for the last 5 minutes. Well, summary, first of all. 3 things I want you to be distinct about. There is the relational model as a theory, or as a proposal. the data structures, the operators, and the integrity rules. So this is the theoretical idea of what the relational model is. Originally, this was defined by Codd in that paper right in the beginning, but then it's had 30, 40 years of development on top of that and embellishment on top of that. So there is, in theory, what is a relational model? The fact that it's built on tables, data types, operators, integrity rules. That's kind of the theory of the relational model. And then we could also add in here the underlying relational logic and things like that as we go deeper into what a relational database is and how it operates. Then we have the software, the relational database management systems that implement the relational model or some of the relational model. And those RDBMSs they don't only implement those models, they also often provide a sets of tools or applications for interacting with that model, with the database, unsurprisingly. So Postgres comes packaged with Postgres PostgreAdmin 3. It comes packaged with all sorts of drivers for accessing the data in the database from various programming languages, etc., etc. There are all sorts of tools and things to help you develop, manage your database. So that's the software. Then, the third thing to identify is that there are the standards. So structured query, SQL, is an international standard syntax, so a language, for implementing and interacting with the relational model. So this is a whole group of people interested in relational databases who've met together and discussed what do we want. Let's come up with this ideal language for interacting with the relational model, and that is the international SQL standard that they've come up with. So they've defined a set of instructions, a set of commands that every relational database they think should implement in using the same terminology as they do. So it's a standard syntax. But relational database management systems, the software, vary in how much of the standards that they implement. So some are, Postgres, for example, is about as compliant as you can get with SQL as you're likely to get. This SQL standard, it's quite compliant. They try and be compliant. But it still have differences. There are still differences in how you write SQL in Postgres to the SQL standard. There are still differences. And those differences represent the historical idiosyncrasies of the software. It's not that they wouldn't like to change them, they probably would, but it's just so deep in the code somewhere, some of these things, that they're not easy to change. So they vary, so the software varies in how much they implement the standards. And we'll have much more on SQL next week. Okay, let's finally, quickly. So in 1985, so this is 15 years after Codd's original paper, Codd wrote another paper reacting to the industry selling RDBMSs that he did not think they were truly relational, whatever that may mean. So what this paper did, or this report that he wrote, he stated 13 rules, numbered 0 to 12, that define a true relational database. And some rules, I hasten to add, are controversial. For example, Rule 3 on 3-valued logic. Rule 0, I'm not going to go through all 12, I'll show you that. The system to qualify as a relational database management sits, that system must use its relational facilities exclusively to manage the database. And if you meet this criteria, then the other, or rules 1 to 10 are then implemented. So by meeting rule 0, you're also meeting rule 10. And it's true that very few relational database management systems comply with all Codd's definitions of what a relational database management system should contain. There are the rules. Please read them in your spare time. I mean, to be honest, I'm not an expert on the individual rules, but you go through those, have a little glance at them, Those are the rules. According to COD in 1985, a relational database should manage all of these. Very few, if any, relational database management systems actually meet all COD's criteria. Is COD being a pedant? Well, you know, he's a computer scientist and things, and that's his stuff. That's what he's interested in. But from a daily basis, we don't really need to know about that. Just bear that in mind. The whole definition of what a relational database is actually quite, you know, it's a bit of a fuzzy affair. It's not a clear affair. Very final thing, limitations. Just remind ourselves that, okay, this is all very good, but not all data is optimally tabular, as I mentioned last week. Difficulties, particularly difficulties in representing sometimes of relationship, particular spatial relationships don't fit well, as I mentioned last week, into the relational model. Also, parent-child relationships require iterative queries which are not supported by SQL. So if you've got a tree-like structure that you're trying to store in a relational database, you cannot write SQL to get results on that. And I know this because I've done it myself. I've written it. I have a database, a Postgres database in which I store tree models. And I had to write iterative queries. My SQL couldn't do the queries. I had to write extended SQL in a programming language embedded. I write functions basically to actually write queries that return tree-based models stored in tables. I'll probably tell you about that in due course. Full formalization in the relational model, full normalization, and we'll get to normalization in due course, can lead to very complex data structures. So sometimes you may actually not want to follow the instructions fully for creating a fully relational model, a fully formalized, normalized relational model, and we're going to get into what this actually means in detail in due course, but there's a sort of theoretical way of arranging your data to optimize the relational model. Well, that may be in theory a good idea for minimizing redundancy and dependency, but it may impact on your, you may end up with a very large, complicated data structures that are slow to query, and therefore your database doesn't scale very well. Scale meaning more records, more people accessing. So there are real limits. While the relational model is highly successful, never forget it has its limitations. Excellent. Any questions? No. Okay, so for this afternoon, if you haven't got a USB stick or your own computer that you want to install Postgres on, then I suggest you wander down to Maplin or whatever down the road over lunch, get yourself a USB stick. I think that's the only thing and we meet again at 2. If anybody fancy coffee? Yeah. Go down to Picton, if anybody's there, have a coffee. And I'll see you at 2 o'clock.